All right, in this explainer, we're diving into some fascinating new research on a really tricky problem. How do you stop stealthy drones? The secret weapon, it turns out, isn't about having better eyes. It's about seeing something the drone absolutely cannot hide, its own heat.
And this is a huge challenge in modern security. You've got these small, commercially available drones that are fast, they're cheap, and they can pose a serious threat in all kinds of situations. The problem is, they are just incredibly difficult to spot and pin down.
And this is exactly why they're such a headache. A drone like this one is often way too small for traditional radar to even notice. And visually, it can just blend right into a cityscape, a forest, or even a cloudy sky, creating a massive security blind spot.
So, let's get into it. What can you possibly do when the threat is basically invisible?
Well, this is where it gets really clever. The researchers behind this study proposed a complete shift in perspective. They basically said, let's stop trying to see the drone and start looking for the one thing it can't disguise, and that's its heat signature. Just look at the difference here. On the left, with a normal camera, a drone is just another tiny speck in a busy background. Easy to miss. But every drone has motors and batteries, and those things generate heat. So on the right, with a thermal camera, that same drone just glows like a light bulb against the cool background. It goes from being nearly invisible to completely impossible to miss.
But just seeing the heat isn't quite enough. The real innovation, the game changer here, is using an AI system to interpret that thermal image in real time. We're not just talking about detecting the drone, we're talking about identifying it and tracking its every move.
So how exactly does the AI turn a simple warm blob on a screen into a locked-on target? Well, it uses a very clever, multi-stage pipeline.
It's basically a four-step process. First, the raw thermal footage gets cleaned up and color-coded to really make the heat differences pop. Then, a powerful AI model scans that image, looking for anything that could be a drone. As soon as it finds a potential target, a second system locks onto its unique heat pattern to track it, even if it's zipping around. And finally, the system calculates the drone's precise location and trajectory. That first AI spotter is a model called YOLO-V8. The name actually stands for You Only Look Once, and it's designed for one thing: pure speed. It scans the entire thermal image in one shot to flag potential drone targets almost instantly. Think of it as the system's first line of defense. But YOLO just finds the general area. To track a really fast-moving object, you need something more. And that's where feature matching comes in, using an algorithm called BRISC. It analyzes the specific pattern of hotspots on the drone, kind of like its unique thermal fingerprint, and uses that to keep a solid lock on it from one frame to the next. This is what gives the system its high-speed tracking chops.
Okay, so the theory sounds great, but the big question is always, does it actually work in a real test? To find out, the researchers set up a nighttime experiment in a controlled 15-meter square area. They flew two different drones. One was just a standard, off-the-shelf model they called the good drone. The other one, the bad drone, they wrapped in aluminum foil. Now, this was a really smart move because it altered the drone's thermal signature. It was a way to test if the AI could not only detect drones, but also tell the difference between them.
So the drones are in the air. What did the AI actually see? And a total success. As you can see right here across these frames, the system draws these bounding boxes around both drones no problem. But, and this is the crucial part, it correctly labels the foil-wrapped one as the bad drone. This proved it could both detect and classify targets based only on their heat signatures. Pretty incredible. So the test was definitely a success, but when you start digging into the performance data, you find some really important trade-offs and a few reality checks about where this technology is today. So the researchers found this interesting trade-off. If you just use the YOLO-8 spotter, it runs at about 78 frames per second, which is great for long-range detection. But if you add that high-speed BRISC tracker, you boost the performance to nearly 100 frames per second, and that extra speed is absolutely vital for tracking fast drones up close. And here's a number that really highlights why the right hardware is so important. The system runs about 2.5 times faster on a dedicated graphics processor unit, a GPU, than on a regular computer processor. That speed boost is literally the difference between a system that works in a lab and one that could actually work in the real world. Now, as promising as this all is, it's not a silver bullet. The paper is very clear about the current limitations.
performance drops off pretty hard beyond about 35 meters. It struggles in daylight when the background is warm, and right now, it's not capable of handling something like a swarm of multiple drones.
So what this research really shows us is a powerful new tool in development, one that can see what we can't. But it also leaves us with this final thought. In the constant cat and mouse game of technology versus counter-technology, the race is always on.